The consolidated PBY-5A Catalina flying boat was one of the most widely used seaplanes and later amphibious planes of World War II. This model is distinguished by its hydraulically actuated retractable tricycle landing gear with the main gear design based on one from the 1920s designed by Leroy Grumman. In this project, we'll be going through the landing mechanism as well as the mechanism to lift the floats of the aircraft. We'll go through an explanation of how these mechanisms actually work, detailed kinematic diagrams, and mobility calculations of the linkages and joints. Here we see an up-close view of the PBY-5A landing gear mechanism. We can see several revolute joints, with two of them hidden up inside the body of the aircraft. Here is a detailed kinematic diagram of the landing mechanism, with the number of joints labelled in red and the number of links labelled in green. The explanation of the landing gear mechanism, as detailed on page 5, line 52, will only be considered in two dimensions, as the mechanism only operates on one plane. In 2D, the whole mechanism has mobility 1, which we will be calculating later on. Our one input parameter, which is the red link, is able to bring the device into any particular position given the constraints. The landing gear mechanism works by using the input link red, which is the hydraulic actuator, to move the wheel, which is the output link in green. As the red piston retracts, the orange and yellow members break at the hinge and fold inwards, while the landing gear, in green, will move upward on a curve determined by the connection points and lengths of the buoy struts. The wheel is completely stowed when the red piston is fully retracted and all the members are flush against each other in the hull. To deploy the landing mechanism, a kick lever is used to push the wheel hub out of the stowed position and allowed to fall due to gravity, whilst being slowed by the red piston.
Here is our 2D mobility calculation for the landing gear mechanism. Over to our left is the kinematic diagram, with in green being the number of links and in red being the number of revolute 1 degree of freedom joints. From the mobility equation, 3n1, take 2f1, these numbers can be plugged in to determine the mobility. That leaves us with one. From the theory of machines and mechanisms by Shigley and Yuga, mobility is defined as the number of input parameters which must be controlled independently in order to bring the device into a particular position. From this equation being 1, this makes sense as a small movement in the length of member 4 will result in the overall mechanism moving.
Similarly, the two-dimensional kinematic diagram for the float mechanism can be analysed for its mobility. Here, the number of links n equals 6 and the number of 1 degree of freedom joints f1 equals 7. Going through the mobility equation, as detailed on page 3, line 33, results in mobility of the float equal to 1, which is consistent with the fact that there is only one input parameter needed to bring the float into any particular position. As explained in page 6, line 68 of the report, the float is connected to the wing by the buoy strut. When the float is retracted, the green strut is pulled inwards towards the fuselage by the red linear actuator in the wing. This causes the yellow and orange members to bend inwards at the hinge and pull the float upwards in a curve until the blue float strut and orange and yellow struts are flat against the bottom of the wing, with the green push rod and connector sitting inside the wing.